Hello students, in previous lecture we have seen definition of subgroups and seen some examples of subgroup. Now we will see next theorem, necessary and sufficient condition for non-empty subset to be a subgroup. Now when we say that H is a subgroup of group G, that H is must be non-empty and H itself a subgroup, then we say that H is subgroup of G. So we will see necessary and sufficient condition, necessary and sufficient condition for non-empty subset to be subgroup. So theorem, so statement of the theorem is that a subset which is non-empty H of group G is a subgroup. G is a subgroup of G if and only if first condition H should be closed. H is closed under the binary operation of G, and H is closed means what? For any, that is for A B belongs to H, then A star B must in H. So second condition, the identity element E of G is in H. The identity element E belongs to H. So means what? Identity element in G is same as identity in H. So third one, for all A belongs to H, it is true that A inverse also belongs to H. This is the inverse element. So this is existence of inverse, existence of identity element. So for all A belongs to H, it is true that A inverse also belongs to H. So we will prove this theorem. Here what is given? A subset H of group G is subgroup if and only if. Here condition is if and only if, means we have to prove this theorem by two way. Means first condition, I have these things. What is the first thing? A subset H of group G is subgroup of G. First what? H is subgroup of G. Then we have to prove that H is closed under star. The identity element E of H, E of G is in H, and for all A belongs to H, it is true that A inverse belongs to H. And second things, we have these three things, and we have to show that H is subgroup of G. So first part we will prove from this condition, we will prove these three conditions, and second part, converse part, from these three conditions we have to prove that H is subgroup of G. So proof. So if part, so let what is given, H be subgroup of G, H is subgroup of G, and H is subgroup. First, what is given? A subset H. So H must be first subset. Now H be non-empty subset of G, and second thing, what is given? H is subgroup. So H is subgroup of G. So H is subgroup of G. So H is subgroup of G means what? H itself forms group. So H itself forms group means what? H is closed. So this is the closure. H is closed under binary operation star. Second one, existence of identity. Third condition is associative. Third, existence of identity, and fourth, existence of inverse. Since since H is itself a group, So here we have first thing, H is subgroup of G if and only if first condition we have to prove, first condition prove that these three conditions, H is closed, the identity element E of G is in H, and for all A belongs to H, A inverse also belongs to H. So since what is given, H is subgroup of G, it must be closed, therefore it must be closed, it must be closed under binary operation star, under binary operation of G. So also identity element E of G is in H, and for all A belongs to H, there exists A inverse also belongs to H, such that A into A inverse, which is equal to identity, then A inverse belongs to H is inverse of A. So first we have things, H is subgroup. H subgroup means what? H itself forms a group, means there exists, it must be closed. So it must be closed under binary operation star, and also identity element, H is subgroup means H itself group, so identity element exists and inverse element also exists. Now conversely we have to prove that. So we have these three things. So first, H closed under operation of G, the identity element E of G in H, and third condition we have A belongs to H, it is true that A inverse belongs to H. We have these three things, so we have to prove that H is subgroup of G. So converse part, conversely, to show, let H be subset of G, which is non-empty subset of G. So furthermore, let H is closed, and for any A belongs to H, so let A inverse belongs to H. So for any A belongs to H, there exists A inverse also belongs to H. So we have these three conditions. So we have to show that H is subgroup of G. So H be non-empty subset of G, and H is closed for any A belongs to H. There exists A inverse belongs to H, such that A into A inverse, which is equal to identity. So to show that H is subgroup of G, so we must check the operation, on H is associative. So H contains the identity element, and every element in H has inverse in H. So H must contain identity element, and every element in H has also inverse element in H. So H contains H the identity element and every element in H has inverse, and every element in H has inverse element. So inverse element in H. So therefore associativity existence of inverse satisfied. Now next is associativity, right? For associativity, for there exist three elements. So if A, B, C belong to set H, then since H subset of G, that implies A, B, C also belong to set G, but associativity holds in G. That implies we say that associativity hold in H, because H is subset of G, and ABC belong to H means ABC also belongs to G, and associativity exists in group G. So automatically it holds in H. So associativity in G holds in G, holds in G. Thus A into B into C is same as A into B into C in H. So this is the property for associativity. Now next we have to check for existence of inverse. Since A inverse belongs to H, and so A into A inverse belongs to H, and H is subgroup. We have to show that H is subgroup. Now, what we have given, H is closed under binary operation star, means what? Any two element from set H, and then their product will get again another element also belong to that set. So we say that A into A inverse belongs to H, and H is closed. It must be true that H is closed means what? A into A inverse. It must be true that A into A inverse, which is equal to identity, belongs to again H. Therefore, so identity belongs to H, and what we say that A inverse is an inverse element of A, and A inverse B inverse element of A. Therefore, all three conditions satisfied, means first all four conditions: first, closeness, associativity, existence of identity, and existence of inverse. All four conditions satisfied, then we say that therefore H is subgroup of G. H itself group, so therefore H itself group, hence H is subgroup of G. So this is the theorem. Means first, from first part we have shown that H is closed, identity element E belongs to H, and if E belongs to H, then their inverse also belongs to H. So we have shown. Now from converse case, from these three conditions we have shown that H is subgroup of G. H is subgroup means H itself forms a group, therefore H is subgroup of group G. Now we will see examples. Find subgroup diagram of group Z4. Find subgroup diagram of group Z4. So to find subgroup diagram, so how many subgroups are there in Z4? So in Z4, what are the elements of Z4? So Z4 has elements 0, 1, 2, 3. So we have to find subgroup, means we have to find possible subset in Z4 such that which those subsets means which satisfy itself group. So first I will take suppose H1, which is again singleton 0. H2 I will take two subsets, so which is 0, 1. Next H3 0, 2, H4 0 3. So these are all subsets of Z4. We have to check that H1, H2, H3 and H4 forms a subgroup. If these are forms subgroup, these are forms group, then we say that these H1, H2, H3, H4 are subgroups of Z4. So first check H1, H2, H3 and H4 are groups. Uh, so we have seen a note in previous lecture that every identity element always subgroup of group G. Here H1 is equal to singleton 0 is an identity element, so which is always subgroup. Now we have to check H2, H3 and H4 are subgroup, means H2, H3 and H4 itself forms a group. So we'll check. So for H2, to find composition table, so here operation is addition, so addition table 0 1 0 1, so addition table 0 1 1 and 2. So here in H2, so I have 1 1 belongs to H2, but operation addition, so 1 plus 1 which is equal to 2, which does not belong to H2, therefore H2 is not group. So closeness property not satisfied, so not closed under addition. So closeness property is not satisfied, therefore H2 is not subgroup. So to check H3, to check H3 is subgroup. So again we will prepare composition table. So under addition operation in H3, so 0 2 0 2 0 2 2 2 plus 2 4, and here mod 4 operation, so 4 plus 4 mod 4 will be 0. So we get in dotted table every element from dotted table are from H3. So H3 is closed. Here H3 is closed under addition, because in dotted table we have we get entries 0 to 0, which is from set H3. H3 will be nothing but 0 to 0 and 2. So H3 is closed. Now Z4 is associative. Z4 associative means we say that H3 always associative. So second condition, Z4 is associative, therefore hence H3 is also associative. So next third condition, existence of identity 0 belongs to S3 is an identity element, and every element has inverse in H3. So that is if element I take element 0 2, so what are the inverse of element? So inverse of 0, what is the inverse? So inverse of 0 is 0, and inverse of 2 is again 2, because if 2 plus something added which is inverse, so 2 plus 2 is equal to 0 means 2 is an inverse of 2, and here 0 plus 0 is equal to 0 means inverse of 0 is 0. So these are two elements, 0 2 has inverse 0 2. So all four properties satisfy means what? H3 itself group, that implies H3 is subgroup of Z4. Now again we will check for 03 H4. So check H4. So for H4, so we will prepare again table. So addition operation. So 0 3 0 3. So addition 0 plus 0 0 3 3 plus 3 6, 6 mod 4, what we get 2. So here in dotted table, so closeness property is not satisfied because so H4 is not closed since 3 and 3 belongs to H4, but 3 plus 3 which is equal to 6, modulo 4 operation here is modulo 4 which is congruent to 2 modulo 4, right? Here modulo 4 operation, so 6 congruent to 4 modulo, sorry, 6 modulo 4 which congruent to 2. So here reminder is 2 which does not belong to given set H4. So uh, operation is not closed in H4, so H4 is not group, therefore H4 not group, therefore which is not subgroup of Z4. So what are the subgroups? How many subgroups we get? So here there are total 1 2 and 3 subgroups. So subgroups of Z4 are singleton 0, next 0 2, and improper subgroups which is Z4. Therefore uh, we we draw the diagram, subgroup diagram. So singleton 0 always contain in both these two sets. So singleton 0 which contain in smallest set 0 2, and smallest set which contain in Z4 is nothing but 0 1 2 and 3. So which is the subgroup diagram. So next we will see the theorem. Let G be a group and A belongs to G, then H is equal to A raised to n such that n belongs to set of integer is subgroup of G and is the smallest subgroup of G that contains A. So theorem, let G be a group and let A belongs to G, then H is equal to A raised to n such that n belongs to set of integer is a subgroup of G and is the smallest subgroup of G that contains A, that is every subgroup containing A, every subgroup containing A contains H. So we have to prove this theorem. What we have given, G be a group and A belongs to G, then H is equal to what? A raised to n, such that n belongs to set of integer is forms a subgroup of G and which is the smallest subgroup of G that contains A. So we will prove this theorem. Proof, as what is given, A be a group, G be a group, G be group, and what is H? H is the thing what? A raised to n such that n belongs to set of integer. Then our claim is, what is our claim? We have to show that H is subgroup of G. So it is sufficient to show that, to prove subgroup test, to prove subgroup test. So what is subgroup test? So we have seen necessary and sufficient condition, that if H is subgroup of G, if and only if first condition H is closed, existence of identity and existence of inverse element. So it is sufficient to show that subgroup test, that is for a subset of group to give a subgroup. Since we have given h always in the form of a raised to n, means I will take any two elements are from set h. So since I will take a raised to r, a raised to s are from set h, then what, a raised to r into a raised to s, which is a raised to r plus h, r plus s, for r and s belongs to what, set of integer, which implies that r plus s again belongs to set of integers. Hence what we say that here a raised to r into a raised to s, which is equal to a raised to r plus s, r and s belongs to set of integer, then r plus s also belongs to z, means what, a raised to r plus s again belongs to what, set h. So what we say that, hence a raised to r plus s belongs to set h, hence h is closed under the binary operation g. Now also for 0 belongs to set of integer such that here n belongs to set of integers, means I will take 0, so a raised to 0 will be what I get, a raised to 0, so a raised to 0 is equal to identity, so e again belongs to h, for I take particular value n is equal to 0 in set of integers, so I get a raised to 0 is equal to identity, so identity element exists in h, therefore identity element exists in h. And second, next condition, to show that there exists an inverse element. So now for e raised to r belongs to set h, then a raised to minus r also in h, therefore a raised to minus r belongs to set h, and so e raised to r belongs to h, a raised to minus r belongs to h. So by closeness property, what we say that e raised to r into a raised to r into a raised to minus r, what will we get, a raised to r into a raised to minus r, which is equal to a raised to, I will take addition of indices r minus r, which is equal to a raised to 0, which is equal to identity, and identity belongs to h, means what we say that a raised to minus r is an inverse element of a raised to r, therefore a raised to minus r is inverse element of a raised to r, hence all three conditions of subgroup test is satisfied, therefore all three conditions of subgroup test is satisfied, hence h is subgroup of g, hence h is subgroup of g. So hence the proof. So we have used the sufficient condition to prove subgroup test, means what, we have h is subgroup of g, then to show that h is closed, there exists an identity element, and last condition, there exists an inverse element in h, means here I have taken two elements from set h, then closeness property satisfied, that's why a raised to r plus h again belongs to h. Next, existence of identity, I will take n is equal to 0 from set of integers, so a raised to 0 is equal to identity element, so which is belongs to h, and there exists an inverse element, means a raised to r belongs to h, a raised to minus r belongs to h, then by closeness property a raised to r into a raised to minus r, which is equal to identity, means what, a raised to minus r is an inverse element of a raised to r, so a raised to minus r is inverse of a raised to r, means all these three conditions satisfied, means what, h is an subgroup of g that contains a. So hence the proof. Thank you.